Good afternoon.
Hi everyone, thank you for having me today, and I'll be presenting my paper, which is Automated Architectural Space Planning Systems, Cognitive Challenges and Opportunities. The paper is divided into a couple of sections. I will start with an introduction, then a literature review, and then I will briefly describe methodology, discussions, and a few closing remarks. A little bit about myself. I'm a computational designer and researcher. I went to Bartlett, and this thesis is part of my master in architecture thesis. It's a sum of my works navigating the domains of body, consciousness, and vision, exploring the technological and spatial protocols between human interactions with computational media. In the thesis, however, I ask questions about the current stage of automated space planning and its relation to ways in which we as designers think and create space. In architecture, the adoption of technology lags behind other sectors, even with advancements such as BEAM or digital twins, and the rise of development platforms such as Grasshopper and Dynamo in recent years. We've yet to see efficient automation in the core design activity, the architectural space planning. Design practitioners are proficient and well equipped to tackle complex design problems, but as humans, we possess finite cognitive abilities, which limit us as problem solvers in domains such as design. Overcoming these cognitive limitations may be achieved through development of computational systems to decrease or replace need for human processing. In fact, various approaches have been explored since 1960s, varying in scope, objective, and efficiencies. Some research focused on single-story layouts using space allocation or shape grammar. Other employed procedural methods, heuristic search, genetic algorithms, fuzzy logic, or more recently, artificial neural networks. Recently, advancements in computer science enabled new machine learning models to combine near real-time analysis and content generation. However, the well-known absence of high-quality datasets might only constitute one aspect of barrier. I propose that one has to consider how the proposed solutions compare to the mental and design models that human designers rely on. So the key three areas of interest are models, natural algorithm models, and artificial or digital algorithm models. And we will look at how they created and used, what constitutes them, and how they relate to design. So cognitive processes build internal representation that interact with our perceptions of external world. Those are very often referred to as models or mental models. These cognitive structures underpin reasoning, actions, and decision-making. And although various models exist, the most common categorization divides them into descriptive, prescriptive, and predictive functions. In design thinking, on the other hand, in your session proposed three model types, two relevant for us, which is the analogical models, formed through analogies, visual, focus on external visual cues, and then simulative, generating new states of existing knowledge. Now, although the presence of the models in theory is widely acknowledged, their direct empirical observation remains challenging. Haynes strongly suggests that models are created through learning. He says that to learn is to form an internal model of the external world. I'm more interested in what a good or what a bad model is. And we learn from Starfield, for example, that the models can only be judged in particular contexts, right? So the efficiency or effectiveness of the model is measured against very specific objectives and goals, with evaluations grounded in validity or utility for a given purpose. All models are imprecise and partial, but what's important is that they are aligned with the user's goals and objectives. The models must also be time efficient and must follow the recognized knowledge conventions within a specific domain they describe. The many of us perceive creativity as an elusive or instinctual activity, but historical explorations into design theory can be traced back to the iconic figures like Vitruvius. And over time, this has led to the formulation of structured design methods, which not only steered or helped to steer the artificial intelligence research, but also lay the foundational principles of system design improvements. And the models per training to design and design process fundamentally spotlight how designers envision and frame their designs. And that's important. Now, let's think about the design problems faced when in design in space planning. The problem solving, as it was mentioned, is a widespread human activity that humans are very well prepared for, and it occurs across many domains. But there are many different types of problems. There are problems like structured puzzles that offer clarity, but others dwell on ambiguity. Some problems are solved using the data provided within the problem itself. Others rely on experience. Generally, design tasks are considered to be on the complex end of the problem spectrum, and literature commonly defines design problems as ill-defined and ill-structured because of the sort of co-evolving constraints and objectives at various design stages. Here we're looking at the very difficult problem of a very difficult puzzle on the left, but a problem that has a very clear stopping point once the puzzle is solved. On the other hand, architectural space planning is a lot more difficult, as the optimal solution is a lot harder to define. The design problems are also described as wicked problem because of the lack of formulation and the stopping rule I've mentioned, and also the literature agrees that there's no single algorithm or strategy to achieve the perfect, optimal solution. Another very important aspect is the knowledge in design, how it's used and acquired. So designers often start the design process with incomplete and changing requirements that shift as the design progresses. And Donald Schoen's contribution to the design theory might be very helpful here, as he focused on the importance of implicit knowledge in design, or he focused on the interplay of intuition, experience, and reflection. Central to these are the three concepts: reflection in action, over here, which underscores the real-time iterative nature of design. And as designers, we immerse ourselves in this problem-solving task as a sort of very dynamic frame, which is sort of constantly recalibrating and being reassessed. There's also a knowledge in action, which encapsulates the repository of experiences and intuitions that designer accumulates over time. It is known as the repertoire of expectations, images, and techniques that becomes the sort of instinctive tool. And there's also a reflection on action, which is a sort of a post-design introspective phase, if you like. The notion of previous knowledge built up and reappropriated for new design challenges have been addressed also by Wilbury and Borrow. They discuss the amplification strategies: the backup, which is the ability to undo previous actions at zero cost; recall, the use of precedents and previously developed ideas; and replay, which is a reappropriation of its ideas as a mitigation of cognitive limitations. Also, the concept of knowledge representation is fundamental to any problem-solving process. Architecture depends on various forms of representation, and Akin, for example, proposed two primary forms. Analogical, which relates to topologically accurate representations of reality, used to analyze and simulate critical design parameters; and the symbolic, so that would be through mathematical formulas, spreadsheets, but also charts and sort of abstractions of designs. So an example of that be a topologically correct, constructible plans or perspective, and the symbolic would be graphs and diagrams, diagrammatic representations. Now I will now go briefly through. Now I'll go briefly through three main methods that are researched in the literature study. So generative adversarial networks, or GANs, are a type of artificial intelligence model consisting of two parts: a generator, which creates the image, and discriminator, which evaluates them. For floor plan generation, GANs can be trained with a dataset of existing floor plans, and then the generator produces new plans while the discriminator assesses their validity. Notably, Nauta et al. Produced two papers in 2 consecutive years, and they propose GAN layout refinement network. This system represents a synthesis of graph constraints, relational GANs with conditional GANs. So it's unique because it allows to produce the initial draft of floor plan design and then interactively refine these layouts. The training data used is an airplane dataset with almost 120,000 floor plans. Evolutionary algorithm is an alternative approach which encompasses actually a group of problem-solving methods that derive complex from roughly biological evolution. These mechanisms select and preserve the best or fittest available solution, and the new solutions are then generated as offspring based on survival parameters, allowing weaker solutions to be replaced by potentially better. This approach, however, doesn't guarantee the finding of top performing solution, but rather it enables users to search for a wide range of possible solutions and then see the direction. Notably, Nishtuk and Mishkovsky used the hybrid of evolutionary and greedy-based algorithm to floor plan generation, and they used the greedy algorithm to recreate architecture process stages. So here is an example of inputs that are introduced to the tool that was released after the paper I'm referencing, but uses the same logic, and it allows the user to input constraints, and then the floor is first generated and then be also represented as sort of three-dimensional. Other approaches included the space allocation and shape grammar algorithm sort of hybrid by Okhoya et al. And they partition according to constraints the space, and then they place inventory using space grammar, shape grammar. And Wu et al. Use learning-based approach, also very large dataset collected from residential in Asia. Now for methodology, the paper proposes comparative analysis ranking selected methods according to 2 dimensions of contrast. First is based on pragmatic requirements of design practice, and the second based on criteria drawn from the mental models. So I'll go through them one by one. This is just a preview, so this is 1 dimension of contrast, and there's the other one, and there's also a ranking of papers. So I will start with modeling dimension, so it ensures that algorithm align with the designer's mental and existing design models. I first start with category, an analogical category. So here on the in the table on the left, we can see 4 possible scores, and analogical constraint emulates or assesses the ability or the capacity to learn and reuse successful solutions. Those are mainly offered by machine learning algorithms, as the early methods use evolutionary logic, which means that every time you start a project from scratch without a prior solution, to base the assumptions or as a benchmark. Although the models don't learn via the analogy, they learn the sort of high-level concepts of generating new instances. Then we have a visual category. which assesses the flexibility of representation. Methods should ideally facilitate the idea of synthesis between diverse representations, like the analog or symbolic or weak and strong. The Nishtigan-Meshkovsky approach is notable with more interactive interface that allows actually to switch between analog and symbolic. There's also a simulative, which maybe we can look at it in a ranking now, which explores the ideas of the user being able to tweak the system parameters. Iterative methods such as those by Nishtigan-Meshkovsky or Wu or Nauta rank high because of real-time adaptability. The evolutionary algorithm provides multiple iterations, allowing a user to edit or to pick the solutions that are the preferred solutions. And then there is also a reflective category, which emphasizes the importance of continuous learning and the system reflection. Evolutionary algorithms, like those by Nishtigan-Meshkovsky, allow user feedback but don't change the future results. Only Nauta et al. Supported ongoing learning. This criteria is least developed across all papers, but holds a great potential for growth. Now, for pragmatic requirements, we have inputs, outputs, accessibility, and time efficiency. And for inputs, we assess how much input the user have for the inputs we assess or we treat inputs. Now, inputs restrict solution to user-defined areas, adjacency matrices, or functional openings or other parameters. And while most methods accept only basic inputs, Nishtigan-Meshkovsky and Nauta et al. Accommodate more complex inputs such as the adjacency constraints and so on. Outputs, most methods provide 2D plans and abstractions, so just rectangular representations. However, again, Nishtigan-Meshkovsky offer 2 and 3D outputs, and also Chaleur showcases plans with furnitures, although those are raster, so not reusable in a sort of conventional architectural process. Accessibility assesses how the user requirements. Some need some papers or some approaches need prospectively a software engineer for a setup, but others might require a computational designer, while some others might be designer friendly. Accessibility combined with visual modeling should align with the design workflows. And finally, the time efficiency, it assesses the time needed for a setup, and manual intensive methods that aren't scalable, like the Sunmes, Hua, or Hoya, are scored lower than for example, the Nauta or the learning-based approach by Wu et al. For that reason. The paper uses mental models, design models, and natural design models as a device to examine the relationship between design practitioner cognition and artificial design algorithm. Machine learning approaches, particularly GANs and deep learning, are more promising for further exploration. However, those must be combined with learning and reflective strategies, such as continual learning, backup, deploy, or recall. Flexibility of representation and simulation models must be considered to ensure compatibility with existing natural models and the dynamic of architectural practice. Algorithms must be evaluated within the context of existing workflows in architectural practice. This paper acknowledges the significance of pragmatic considerations as emphasized in many previous studies. However, it also stresses the importance of addressing natural cognitive processes in relation to technical challenges. The scope of this paper does not exhaust the domain by any means, but should serve as a catalyst for further exploration at the intersection of cognition and space planning algorithms. Thank you very much.